Let's quickly discuss answers to the worksheet questions. So one of you tell me, what is the basic formula for dot product of two vectors? What is, or how do you calculate A dot B?
Sir, AB cos theta.
AB cos theta. Okay. Small a is the magnitude of the vector A. Small b is the magnitude of the vector B, and theta is the angle between them. Fine. So you can also write this as A multiplied with B cos theta. This was all there in the worksheet. So which is basically A multiplied with the component of B parallel to A, scalar component of B parallel to A. You can also write this as B multiplied with A cos theta, which is B multiplied with the component of, or the scalar component of A in the direction of B. Okay, right. First question, diagram is given to you. Tell me, what is the scalar component of A in the direction of B?
12, sir.
12. You calculate it as A cos theta becomes 20 cos 53 degrees. Cos 53 degrees is 3 by 5. This becomes 12 units. Okay. So indirectly what you found is this. Okay, this will be 12 units. Next, second part of the question, scalar component of B in the direction of A, 15 cos 53.
9.
To 3 by 5 becomes 9 units. So what you found out is this length. Right. Next, you are given a set of vectors. First, scalar component of A in the direction of B. One of you tell me, how much is the angle between A and B?
143.
180 degrees minus 37, 143 degrees can be written as 90 degree plus 53 degrees. Or you can write 180 minus 37 also, whichever way you are comfortable you can. Now, if you need scalar component of A in the direction of B, the formula is A cos theta. The magnitude of A here is 10 units multiplied with cos 90 degree plus 53 degrees. And this was given to you in the worksheet. Use cos 90 plus theta is equal to minus sin theta. Okay. So this becomes 10 multiplied with minus sin 53 degrees, because cos in the second quadrant becomes negative. And sin 53 is 4 by 5. 10 into 4 by 5 becomes minus 8 units. Now, what is this minus 8? Okay, listen. If you take component of A along the direction of B, now clearly A is kind of pointed away from B. So if you drop a perpendicular onto the line along which B is acting, the component of A parallel to B is in a direction opposite to B. That is what the minus suggests. And its magnitude is 8 units. That's what we found out. Okay. Now don't say this is the positive x-axis. Why are we writing minus here? The minus is relative to the direction of B. It has nothing to do with the x-axis. Okay. And you were given in the worksheet dot product. The result of dot product is a scalar. It's not a vector. Okay. So this minus does not indicate a direction. Okay. Similarly, you can find out the others, not difficult. Next, you are given the formula dot product A dot B is AB cos theta. Magnitude of one vector and scalar component of the other vector in the direction of the first vector. A multiplied with B cos theta or B multiplied with A cos theta. Any one of them you can take. Next, you are asked to find out A dot B, B dot C, C dot A. That is easy only. Next, suppose the magnitudes of two vectors are both non-zero. When does their dot product become 0? What is the answer to this?
When the angle is 90 degrees.
Yeah. The formula for dot product is AB cos theta. Rishi, don't answer. You are in 12th class, so this will be comfortable for you, but the others should answer. A is non-zero, B is non-zero. Okay, you can write it as small a, b also, nothing wrong in that. But we want this product to become 0. That is possible only when cos theta becomes 0. And for what angle is theta 0? Theta should be 90 degrees. Okay, so any two perpendicular vectors, their dot product is 0. That's the way dot product is defined. Okay, next. Suppose A and B are two non-zero vectors. Theta is the angle between them. Then if theta is acute, what will A dot B be? Answer. Pawan, what is the answer?
Sir, AB cos theta.
AB cos theta is the formula. I am asking you, okay, if theta is 90 degrees, will it be positive, negative, or 0? Okay, I should have mentioned that. Answer in terms of positive, negative, or 0.
Sir, if theta is 90 degrees.
Theta is less than 90 degrees, first case.
Positive.
Positive, correct. AB, cos of an angle less than 90 degrees is a positive value. Now, AB here are magnitudes of vectors A and B. Magnitude of a vector, magnitude of a non-zero vector is always positive. Okay. So A and B are positive values. Cos of an angle less than 90 is also positive. So if theta is less than 90 degrees, if two vectors make acute angle with each other, the dot product will be positive. If angle is 90 degrees, which is discussed, the dot product will be 0. And if angle is greater than 90 degrees, then AB cos an angle greater than 90, cos of an angle greater than 90 degrees will be negative. So the whole thing will become negative. So dot product of two vectors which have an angle more than 90 degrees between them is negative, will be negative. Okay. If the magnitude of a vector capital A is small a, then how much is A dot A? Answer, anyone?
A square, sir.
See, both vectors are same in this case. Magnitude of first vector is A. In place of B also you have A. So magnitude of second vector is also A. And what is the angle between a vector and itself? 0. So A cos 0. Cos 0 is 1. So the answer becomes A square. That is square of the magnitude of vector A. That's all. Next, I cap, j cap, k cap are units, you know that. Then how much is I cap dot I cap? So in this case, you will treat I cap as the first vector and the other I cap as the second vector. And what is the angle between them? I cap, it's the same vector, then angle is 0. And these are unit vectors, so magnitude is 1. So answer will be A, B, cos theta. Answer will be 1. I cap dot I cap is 1. Similarly, j dot j, k dot k will also be 1. Next, I cap dot j cap. I cap is unit vector along the x-axis, j cap is along the y-axis. Their dot product will become 0. The other three cases will be 0. Next, using the basic formula for dot product, calculate these. Okay. The first one, if you see, 4 I cap dot 2 I cap. 4 I cap, treat it as the first vector. Its magnitude is 4 units. I cap is a unit vector. 4 I cap will have a magnitude 4 units. Next, 2 I cap will have a magnitude of 2 units. That's the second vector for us. And 4 I cap is along the positive x-axis. 2 I cap is also along the positive x-axis. The angle between them is 0. So 4 I cap dot 2 I cap becomes A, B, cos 0. Cos 0 is 1. 4 into 2, the answer is 8. Okay. Now, all of you who have sent me the answers to the worksheet, I think you have answered correctly. All others will be 0. Why? Next is 4 I cap dot 5 j cap. 4 I cap is in the x direction, 5 j cap is in the y direction, angle is 90 degrees, dot product becomes 0. In all other cases, the vectors are perpendicular, the dot product will be 0. Okay. So I hope you all understood how to calculate dot product of vectors. Let's take this a little further. Suppose you are given two vectors like this. Let's say A is equal to some AX I cap plus AY j cap. It has its own components. Okay. And the vector B is some BX I cap plus BY j cap. It has its own x and y components. And you have to calculate A dot B. Okay. And remember, always read this as dot. Don't say A into B, and always write it also as a dot only. You are not supposed to write like this. This is wrong because there is another way of multiplying vectors called the cross product. Okay. So if you write it this way, if an into is placed between two vectors, you consider it as, or in a standard way, it is considered as cross product. So if you want to indicate dot product, you have to put a dot only, and you have to call it dot only. Don't say into or anything else. Okay. Now you need to evaluate the dot product between these two vectors. First is ax I cap plus ay j cap. Anyway, for dot product, it doesn't matter which vector you take first. Bx I cap plus by j cap. Okay. Now generally, any one of you tell me, suppose you have to multiply a plus b with c plus d. How do you do this? Yusuf, how do you evaluate a plus b into c plus d? You unmuted, but I don't hear anything from you. Okay, you can type your answer. Aishwarya, how do you evaluate a plus b into c plus d?
So AC plus AD plus BC plus B.
You take the first term from the first bracket, multiply it with both terms of the second bracket. Then you take the second term of the first bracket, multiply it with all terms of the second bracket, and so on. How many ever terms are there? Each term of the first bracket with every term of the second bracket is what you need to do. Okay, we do the same here also in dot product of vectors. So what you will be doing effectively is ax I cap dot that second vector, bx I cap plus by j cap, and then ay j cap dot bx I cap plus by j cap. Okay. Now let us evaluate the dot product between each term separately. So dot product between this and this, then the dot product between this and this, and next dot product between this term and this term, and then the dot product between this term and this term. Okay. Look at the first two terms, ax I cap dot bx I cap. Now I cap, they are both in the same direction. So angle between them is 1. And their components, if you see, one is ax, the other is bx. You multiply them, it becomes ax bx times I cap dot I cap. You can write it like this. And we know I cap dot I cap is 1. So the first term becomes ax bx. Next, ax I cap with by j cap. Can one of you tell me what the result will be? Ax I cap dot by j cap.
0, sir.
Why?
Sir, I cap and J cap are perpendicular.
Perpendicular, because the angle between them is 90 degrees, the dot product becomes 0, correct? So the second term becomes 0. Next, the other bracket. Pawan, you tell me, ay j cap dot bx I cap. How much will that be?
0.
0. Because ay j cap is in the y direction, bx I cap is in the x direction. The dot product has to be 0. Aishwarya, tell me the last part. Ay j cap dot by j cap.
Sir, AY BY.
Ay by multiplied with j cap dot j cap actually, and j cap dot j cap is 1. So ay by. So finally, what is the result we get? The product of their x components plus the product of their y components, ay by. Okay, so if you are generally given two vectors like this in terms of I cap j cap, okay, this is how you evaluate their dot product. A dot b is equal to the product of their x components plus the product of their y components. And remember, the result of a dot product is a scalar value. There should not be any I cap or j cap placed in this. Okay, anyway, we'll apply this many times. You'll get used to it. So if vectors are given in component forms in terms of I cap, j cap, k cap, this is how you evaluate the dot product. Had there been a third component k cap, you would have gotten plus az bz. Okay, I mean plus the product of their z components. That's all. Okay, solve this quickly, all of you. Type your answers in chat. Evaluate A dot B. Send answers to both parts together. I got one answer as 10 I cap plus 4 j cap. I was just telling you the result of a dot product is a scalar. There won't be I caps, j caps in the answer. Okay. Aishwarya, Vanilla, Pawan, your answers are correct. Solve carefully, all of you. Multiply the x components and add that to the product of y components. That's all. Use of how much will the dot product be in the first case? And from next class, you ensure that your microphone is working properly, because if we interact directly, it will be better. Anyway, see, you have to multiply the x components of the vectors. 2, 5 becomes 10. That is ax, bx. X component of A multiplied with x component of B. Plus, multiply the y components now. Ay is 4. Before by you don't see anything. That means there is a 1 here. Okay, only j cap means 1 j cap. So 4 into 1. 10 plus 4, the answer is 14 in the first case. Second case, ax, bx. 4 into minus 3, that is minus 12. Plus ay, by, 3 into 4 is plus 12. The answer is 0. Okay. In the second case, we are finding that the dot product of two vectors is 0. When does this happen? Or what does this mean? Anyone?
The angle between them is 90 degrees.
Correct. That means the vector A is perpendicular to the vector B. Okay. You can find out if two vectors are perpendicular by looking at their dot product. Dot product will be 0 only when vectors are perpendicular to each other. Or at least one of the vectors should be 0, but that is not the case here. Both are non-zero vectors only, but their dot product is 0. It means they must have been perpendicular to each other. Okay. Anyway, you'll understand why we need dot product for this chapter. Let us get into the physics part now. Work, energy, and power. Basically, what you'll be learning in this chapter is the definition of work. What work does to a system. Okay, that you will learn. And you all must have heard of this quantity called energy. Okay, and you all must have had some understanding also. There are different types of forms of energy. Energy can be converted from one form to another. Okay, and in lower classes you must have learned the definition. Energy is the, like, can any of you define energy? Just tell me the definition that you learned in lower classes. What is
Sir,
energy?
the ability to do work.
Ability to do work or the capacity to do work. Correct. Okay, so depending on the energy of a system, we can tell how much work it can do, or depending on what happens to a system, we can tell how much work has been done on it. Okay, so from this chapter onwards, we'll start looking at systems from an energy point of view also. What energy transfers are happening? Does the system even have the energy to undergo a certain process? We'll be thinking in terms of energy. Okay, right. Can any of you define work? Okay, fine. Even if you don't know the definition, it's okay. But one of you tell me, like, I'm sure you all must have done work, right? So one of you tell me, when you do work or when you do a lot of work, how do you feel?
Tired, sir.
If you do a lot of work, you feel tired. Your feeling tired means what happened to your energy levels? Increased or decreased?
Decrease.
Decreased, obviously. Okay. So if you do work, okay, let me write it here. Your energy decreases. Okay. I'm sure you all must have heard the law of conservation of energy. Can any of you tell me the law of conservation of energy?
Energy can neither be created nor be destroyed.
In lower classes, whatever you learned, energy can neither be created nor be destroyed, but it can be converted from one form to another. It can be transferred from one object to another object also. Okay. So your energy is decreasing. Does that mean energy disappeared? No, energy cannot disappear. Energy cannot be destroyed. Okay. It means energy got transferred to something else. Okay. So understand the meaning of work. If you do work, your energy is decreasing, means energy is getting transferred. Okay, that is the definition of work. Work is nothing but transfer of energy from one system to another system, or from one object to another object, or within an object or within a system also, from one particle to another particle. If energy is getting transferred, you can say work is being done. Okay. Now, the proper definition of work. Suppose there is an object. It could be any object. Assume there are some forces acting on it. There could be only one force acting. There could be multiple forces acting. Now, if you need to transfer energy from one system to another, in fact, I should say, if you need to transfer mechanical energy from one system to another, okay, a force must be involved. Fine. A force is needed to remove energy from one system and give energy to the other system. So basically, work is done by forces. Work is done by forces. So whenever you are asked to calculate work, you should be specified work done by which force you are expected to calculate. Okay, so remember, work is done by forces. Forces transfer energy from one system to another system. Of course, there are other modes of transfer of energy also. Without force also energy can be transferred, but in that case it won't be called as work. If transfer of energy happens through forces, you call it work. Okay. So assume there are some forces acting on this object. There could be one force or many forces. Work done by force is what we are interested in this chapter. Okay. So let this be one force, F1. Let this be another force, F2. And so on. Gravity could be acting, anything could be happening. And under the influence of these forces and due to its own inertia also, let's say the object undergoes some displacement. Assume this is the displacement of the object. Fine. Then if you want to find out how much work is done by each of these forces, How much work is done by F1 in this process? How much work is done by F2 in this process? Work done by F1 is calculated as F1 dot S. Work is calculated as the dot product between force and displacement. Okay, that's the basic formula for work. Okay, in lower classes, you might have learned it as force into displacement, something like that. From now onwards, you will never use the word into between two vector quantities. It will either be dot or cross. Cross you'll learn in the next chapter. Work is the dot product between force and displacement. Okay, so if you want the work done by the force F1, then it is F1 dot the displacement. If you want work done by F2, that will be the force F2 dot the displacement. Okay. Can one of you tell me what S here stands for?
Displacement, sir.
Displacement of
Block.
the block. So you are saying displacement of the object. Okay, fine. Now you all tell me, is it compulsory that every particle of a system always gets displaced by the same amount? Indirectly, what I'm asking is it possible for different particles of an object to undergo different displacements? You think of some objects, moving objects around you, and tell me, is it possible that different particles of an object, of a single object, undergo different displacements in a certain interval of time? Saket, what do you think? Or Rishi, what do you say?
Sir, on a whole, the distance should be the same. But if there's something moving inside the thing, then it has to be.
Okay, so within the object, if there is movement happening, then you say displacements can be different.
Yes, sir.
Okay. Aishwarya, what do you say? So Rishi, do you mean that it should be a fluid system?
Not really, sir.
You said within the system, particle should be moving. That means it's a fluid. Or
What if there's like a box of marbles in it and it's moving?
okay, fine. So, okay, you're taking a collection of objects as the system. No, not an issue. Vanilla, what do you think? Is it possible for different particles of a system or object to undergo different displacements?
No, sir.
Okay. Actually, the answer is yes. Even in a perfect solid object, it's possible for different points or different particles to undergo different displacements. Okay, for example, consider this pen itself. Suppose I hold the pen here exactly at the center and I rotate it. Okay. If I rotate it, you see this end of the pen, it is going to move up. So it has a kind of positive displacement. The cap of the pen is going down. It has a negative displacement. Are their displacements different or not? They are different. And the center of the pen where I'm holding is not even getting displaced. Its displacement is 0. This end's displacement is positive. This end's displacement is negative. Okay. Fan also you can see. So basically in systems which undergo rotation, system, I should not use the word system actually, solid object. Pen is a solid object. Okay, it's not even like a collection of separate particles. These particles are fixed rigidly to each other. Okay, it's a solid object. In a solid object also, if rotation happens, different particles can undergo different displacements. Fine. So it's possible that different points of an object undergo different displacements. Now we define, like, the formula for work that I have shown you here is force dot displacement, and you know we took S as the displacement of the object here. But now we understand that the entire object need not undergo the same displacement always. Fine. Different particles of a system or of an object can undergo different displacements in a certain interval of time. Okay. Then if that is the case, how do we calculate work done by a force? Which particle's displacement should we take? The answer is, if you want to find out work done by a force F1, okay, you need to take F1 dot S, where S is the displacement of the particle on which the force F1 is acting. Okay, so you have to see how the point of application of the force is getting displaced. Based on that, you can calculate work. But see, this happens in solid objects. This happens, what happens? Different particles having different displacements. This is possible in a solid object when the solid rotates. Okay, for now in this chapter, we are not going to consider rotation. So displacement of every particle of the object will be equal to the displacement of the object as a whole. Okay, but remember the actual formula. In the actual formula for work, S is the displacement of the particular point at which the force F is acting. It doesn't matter what the other points are doing. It doesn't matter what else is happening with the object. For example, like in this case itself, I am holding the pen. If I'm holding the pen, it means I'm exerting a force here. The finger with which I'm holding it, or the two fingers with which I'm holding it, they're exerting some force there. Now, assume the pen moves like this. Clearly it is rotating, you can see. Fine. Different particles of the pen are undergoing different displacements. Tell me, what is the displacement of this particle where I am exerting the force, where my fingers are exerting the force? In this process of rotation, what is the displacement of the particle where my fingers are exerting the force?
0, sir.
0, it's not moving at all. The other points of the pen are moving, but this particular point is not moving. Then if that displacement is 0, that means the work done by the force that my fingers are exerting there is 0. Okay, I'm exerting a force on it, but it's not doing any work because the point where the force is acting is not even getting displaced. Okay, this other force that I'm exerting with this black pen, that could be doing work because the point where I'm exerting the force is getting displaced. So this force could be doing work, but this force that I'm exerting with my fingers at the center of the pen is not doing any work. Okay, so it's possible that different particles of a system undergo different displacements, especially in a solid object. That happens when the solid rotates. If there is no rotation, then every point of the system undergoes the same displacement. Okay. Next. It's also possible that during that displacement, the force varies. Okay. Like suppose you are trying to drag an object. Initially, you may drag it gently. Later, you may drag it with a greater amount of force. Okay. And if you want to calculate how much work you have done, what magnitude of force will you take? Will you take the initial magnitude that you applied or the final magnitude that you applied? You can't take any one magnitude like that. Okay. Then in that case, okay, in general, work done by a force is calculated as, or you can think of it this way. For a small displacement ds, you all know ds is so small a displacement that you cannot even tell how much it is. Okay, it tends to 0. It's not equal to 0, but it tends to 0. For a small displacement ds, any force F can be assumed to be constant. Okay, see, for the overall displacement, let's say of 10 meters or 20 meters, the force may have changed, okay, from point to point. But for a small displacement ds, you can assume the force to be constant. For the next small displacement, you can assume some other force. The displacement after that, you assume some other force, and so on. But for one small displacement ds, even if the force is generally variable, you can assume it to be constant. Then in that case, the small amount of work done, dW, can be calculated as F dot ds. Okay, force dot displacement only. And if the force is constant for the displacement ds, so F dot ds will give us the work done in that small displacement. Now in a small displacement, small transfer of energy only will happen. So small amount of work dW will be done. And if you want the total work done, as the variable force takes the object from one place to another place, you'll have to add all the small amounts of work done. So you'll have to take integral F dot ds. That will give you the work done by a force in general. In this formula itself, if the force is constant, then you can say that work is constant, can be kept outside the integral. It will become F dot integral ds. Integral ds is nothing but the total displacement, and that changes to F dot s. Okay, so remember, F dot s is applicable only if force is constant. Generally, this is how you calculate work. This is always valid. Whether the force is constant or variable, this is one formula for work which is always valid. If it's constant, you can put force outside the integral, otherwise don't put. Okay, so remember, to calculate work done by a force, you need to know how much is the force. You need to know how much displacement the point of application of force is undergoing. And you also need to know the angle between the force and displacement, because to evaluate dot product, okay, W is equal to integral force dot small displacement. And you know the formula for A dot B, AB cos theta. So here it becomes F ds cos theta if the force is variable. Okay, if force is constant, then work can be calculated as F dot s, which becomes Fs cos theta. Magnitude of force, magnitude of displacement, cos of the angle between them. So you can even think of work like this: force multiplied with displacement parallel to the force. Or you can also take it as displacement multiplied with force component parallel to the displacement component. So the mathematical definition of work would be this: the product of force. When you say force, it's only the magnitude. Okay, and the component of displacement in the direction of force. Okay, now why does the component of displacement in the direction of force only matter? Or why does the component of force in the direction of displacement only matter? Let us understand this. Now think about it this way: suppose there's a particle. Assume it is moving in this direction. Moving means velocity is this way, and if velocity is this way, displacement also will be this way itself. Okay, velocity tells you the direction in which the object is moving. So if velocity is to the right, it means object is moving to the right. Fine. Let's say there's some force acting on this object, F. You can resolve the force into two components. One component parallel to velocity. Let's call it F parallel. This provides tangential acceleration to the object. You can take another component perpendicular to velocity, F perpendicular. This provides radial acceleration. Now, one of you tell me, what does radial force do to an object? It provides radial acceleration, okay. But because of that, what happens to the object? What does radial force or centripetal force do to an object?
Sir, it changes the direction of motion.
Changes the direction of motion. It enables the object to take a turn. Correct. Now one of you tell me, what does tangential force do to an object?
Increases the speed of the object.
Increases or decreases the speed of the object. It changes the speed. Now see, tangential force changes speed. Changes speed means it can make the object go faster or go slower. Means it can give energy or take energy away from it. Perpendicular force does not do anything in terms of energy. It doesn't make the object go faster. It doesn't make the object go slower. So that component of force is not involved in the transfer of energy. Okay. Parallel component changes speed means it gives or takes energy from the object. Okay. Give also is there, no? So gives or takes energy to or from the object. And giving or taking energy is what we mean by doing work. Okay. That means this is the component which does work. That is why in the calculation of work, we only need the component of force parallel to displacement. Okay. And that is why in the calculation of work, we use dot product. Dot product ensures that you take magnitude of one vector and the parallel component of the other vector in the direction of this vector. Okay. So from now onwards, never say work is force into displacement. That is a meaningless statement. You have to say force dot displacement. You can tell displacement dot force also, doesn't matter. Okay. And I hope now you understood why it should be the dot product, why we need parallel component. It's the tangential force which increases or decreases the speed of an object or a particle. So it's always the tangential force which can give energy or take energy. Okay. To or from an object. That is the component which will be involved in doing work. Okay. Right. So let's solve some problems now. Assume a block is placed on the floor. And okay. Very recently we had covered friction also, so I'm sure you all are in touch with the formula. Tell me the formula for kinetic friction.
K into N, sir.
Mu k into n. Okay. Let's say this is a 2 kg block lying on a rough surface. The coefficient of friction between the block and the surface. See, when only one coefficient of friction is given, no, use the same for static friction and kinetic friction. Let's say coefficient of friction is given 0.4. And the block is being dragged with a force of some, say, 20 Newton. This is an additional force on the block. Tell me, will 20 Newton be able to slide this block or not? In case it had been in case it was at rest initially, can 20 Newton slide this block or not? Pawan.
Yes, sir, it can.
How did you decide?
Sir, frictional force हमको नहीं है.
Limiting friction. Okay, 20 Newton has to be stronger than the limiting friction on this block. Now we know that limiting friction is given by mu s into n. How much is the normal force on this block? Anyone?
20 newtons.
Its weight is 20 Newton and the other 20 Newton doesn't have a vertical component. So normal force has to balance all the weight. So normal force will also be 20 Newton. And if that is the case, then limiting friction will be 0.4 into 20. That is only 8 Newtons. But the force trying to slide the block is 20 Newton. It will definitely slide. Okay. So you know all the forces that are acting on it. Gravity is acting, normal force is acting. This additional force F that we are applying is acting, and it's a rough surface on which it is being dragged, so friction will also act. Okay. If the block slides by, let's say, 3 meters, okay, it continues sliding after that also, but in a displacement of 3 meters, calculate work done by each force acting on the object. Okay, there are 4 forces acting on it: weight, normal force, the force of 20 Newton, and friction. In a displacement of 3 meters, which way will the displacement be? To the right. Okay. So in a displacement of 3 meters to the right, find out the work done by each of these forces. Listen, all of you, there are some things you need to keep in mind while calculating work. Basically, the formula involves dot product, and the general formula is integral F dot ds. If the force is constant, you can use the simplified version F dot s. So you think for yourself whether these forces are like any force whose work you are trying to calculate. Think for yourself whether that force is going to remain constant throughout the journey or not. If it remains, then you can use the simple formula F dot s. Otherwise, you'll have to integrate. Okay. So try this, all of you. Displacement is given 3 meters. And type your answers in chat. Type your answers in this order. Work done by the force F first, then work done by weight, then work done by normal force, and then the work done by friction. Okay, Pawan, all your answers are correct. Vanilla, one of your answers is wrong. Saket, one of your answers is wrong. Yeah, now your answer is correct. Saket, no, that is not the correction you were expected to do. Okay, let us discuss. Aishwarya, can you unmute?
Yes, sir.
Huh. First, you are asked to calculate work done by the force of 20 Newton. Tell me, is this a constant force or a variable force?
So constant.
It acts throughout the displacement. It's a constant force. So what formula are you going to use to calculate work?
Sir, Fs cos theta.
F dot S, that is Fs cos theta. Okay. Since the force is constant over the entire displacement, you can use this formula. So it becomes magnitude of force, magnitude of displacement, cos theta. Okay. How much is the magnitude of the force whose work you need to calculate?
Sir, 20 Newton.
20, direct. The point where that force is acting, how much displacement is it undergoing?
3 meters, sir.
Okay. Now all of you observe, this is a solid block and there's no rotation involved. Okay. Its orientation doesn't change. With the same orientation, it slides forward. Okay. We call this as translatory motion. There's no rotation involved. And in this chapter, we are not going to consider rotating bodies also. So every point of the object undergoes the same displacement. Only then the object can stay together. Okay. If some particles undergo one displacement, some particles undergo another displacement, then the object will either get stretched or compressed. That is not happening here. Means every particle has moved in the same manner. Okay. So the displacement is 3 meters. Cos. What is the angle between the force and that displacement?
Sir, 0 degree.
0 degree. They are both in the same direction. Cos 0, 1. So the answer becomes 60. Now one of you tell me, to calculate work, we are multiplying force and displacement. Okay. What is the SI unit of force? SI unit of force?
Newton, sir.
Newton. Displacement?
Meter.
Meter. So the SI unit of work should be Newton meter, which is what we call as joule, denoted by the symbol capital J. Okay. Joule is the SI unit of work. You can write Newton meter also, but we use this unit Newton meter for another quantity called torque, which you will learn in the next chapter. So for work, you should avoid using Newton meter, write it as joules. So the force here was in newtons, displacement was in meters, SI units. So the work that you get will also be in SI units. The answer is 60 joules for the first part. Okay, hope you all understood. Rishi, any doubt in this?
No, sir.
Yusuf, any doubt? Okay. Next, work done by weight acting on the object or weight of the object. Second part. Pawan, you tell me, how much is the weight of this object?
The 2 kgs.
Yeah, 2 kg is the mass.
20 newtons.
Weight is 20 newtons. Will it be constant as the object moves forward or not?
I said it's constant.
Weight is a constant force in this case. So you can again use the formula F dot S. See, while solving problems, all this thought process should go on in your mind. Is the force constant or not? Based on that, you should decide which formula to use. Don't blindly write steps. Okay. Fine. The force weight is 20 newtons. Now, actually, weight acts on every particle of the object. The weight of all particles combined is 20 Newton, and the displacement of all particles combined is 3 meters. Okay, so you can take displacement as 3 cos. Pawan, tell me what is the angle between weight and displacement?
90 degrees.
How much?
90 degrees.
90 degrees. Correct. Weight acts vertically and the displacement of this object is horizontal. 90 degrees. Cos 90 degrees is 0. Therefore, the work done by weight is 0 during this displacement. I am not saying weight will never do work, but on this object during this displacement, weight is not doing any work. Okay. Next, work done by the normal force. Now, as the surface remains horizontal, normal force will always have to balance weight. The normal force will always be 20 and it will be constant. So we can again use the same formula for work done by normal force as well. It's 20. Displacement of the block is 3 meters. Cos. Use of what is the angle between normal force and the displacement? – 90 degrees, correct. So the work done by normal force also becomes 0. So it is acting on it. It is normal force is acting on the object, but it's not doing any work. Okay. Finally, work done by friction. Vanilla, you tell me, as the block slides forward, how much friction acts on it and in which direction?
8 Newton towards the left side.
What kind of friction will it be?
Kinetic friction.
Kinetic friction, correct. The block is being dragged on the floor. So the force acting, the frictional force acting on it will be 8 newtons this way. Because it is being dragged to the right, friction acts to the left. 8 Newton. And it's a constant force. Okay, because throughout the journey, normal force doesn't change, coefficient of friction doesn't change. Then friction itself won't change. So again, F dot S can be used. Friction is 8 newtons. Displacement is 3 meters. What is the angle between friction and displacement? Anyone?
180.
180 degrees. And cos 180 degrees is -1. So it'll be the work done by friction will be minus 24 joules. Now observe this. We got work done by one of the forces as negative. Okay. I told you at the beginning that work is nothing but transfer of energy. Now see, this force 20 Newton is trying to move the block. Is trying to slide the block, means it is trying to increase its speed. 20 Newton is increasing its speed. Means it is giving energy to the block. What is friction doing? Tell me, one of you, in this situation, is friction trying to speed up the block or slow down the block? Is friction trying to speed up the block or slow down the block?
Sir, slow it down because it has to prevent sliding.
Correct. Friction's job is to prevent sliding, and in this case, to prevent sliding, it has to slow the block down. So what it is doing, it is reducing the speed, means it is removing energy from the block. That is why, or that is what the negative sign in work done by friction means. Okay. In this case, friction is removing energy from the block. That's why the work done by friction is negative. The 20 Newton force with which we are dragging the block is giving energy to the block. That's why work done by that force is positive. Okay. So remember, when a force does positive work on something, it means it is giving energy to that thing. When a force does negative work on something, it means it is taking energy away from that thing. Okay. Let's consider another situation. Fine, sliding down an incline. I think you all can manage that. Just a moment. Okay. Let's say block of mass 2 kg released on an incline, angle of inclination 37 degrees. We'll just take some comfortable values and let this height be 12 meters. 12 meters is the vertical height of that incline. Block is released from there, and coefficient of friction, if you tell me when will the block slide? When mu is greater than tan theta or mu is less than tan theta?
Less than tan theta.
Less than tan theta. Okay. No. Yes, mu is less, tan theta is more, means angle is too much. Correct. Tan 37 degrees, 3 by 4 is 0.75. Let's say mu here is only 0.5. So clearly it is less than tan theta. The block cannot stay at rest. It will slide down. And as it slides down, you know what all forces act on it. Weight will be acting. Normal force will be acting. And friction will be acting. Calculate work done by each of these forces as the block slides to the bottom of the incline. Start solving. Any answer, anyone?
What is joules?
Work done by what is 240?
Work done by weight.
Wait. Okay, we'll see. We'll see. Listen, all of you. This block we know is going to slide along the incline. So it's easy to visualize its displacement. Can one of you tell me the magnitude of its actual displacement along the incline? How much is the block going to slide?
Sir, 20 meters.
20. How did you calculate?
Sir, sin 37 is equals to 12 by x.
Correct. Opposite by hypotenuse. This slant length, that is the actual displacement of the block, let's call it S, is the hypotenuse of this right angle triangle. Okay, and you know the opposite side 12. So sine 37 degrees, 3 by 5 is 12 divided by S. So you get S as 20 meters. That's the displacement done. Okay. Now there are few forces acting on it: weight, normal force, and friction. Its weight, you know, is 20 Newton. Weight acts this way. If you want, you can resolve weight into components. Otherwise, you can leave it as it is. We'll do it both ways. Okay. Next force is normal force. Normal force acts like this. And as the block slides down the incline, there will be friction acting on it. Friction will act up the incline like this throughout the journey. Okay. The block is going to slide along the incline only. So final position of the block, just a moment. Final position of the block will be this. Somewhere here, somewhere about here. Throughout the journey, the normal force, friction, they would all have acted in the same direction. Okay. First, let us try to find out work done by weight, gravity. Weight of the block is a constant force or a variable force? Anyone?
Constant force.
Weight is a constant force. The block's mass is not changing. Why should its weight change? Okay. As I said, there are two ways to calculate work done by weight. You can take the force as it is and calculate the work done, or you can take its components and calculate work done by each component separately. Okay. Let's do it by taking the force as it is first. Work done by weight. It's a constant force, as you all know. So the formula is Fs cos theta. How much is the weight of the block? 20 Newton. How much is the displacement the block undergoes? We used that. We found out it is 20 meters. We used trigonometry and calculated it as 20 meters. Okay. Now, Rishi, tell me, what is the angle between the actual weight of the block and this displacement? How much is this angle? Aishwarya, you tell.
So 53 degrees.
It will be 53 degrees. So the angle between weight and the displacement is 53. So you'll have to take cos 53 degrees. And cos 53 degrees is 3 by 5. 20 to 20, 400 into 3 by 5. 400 into 3 is 1200 divided by 5 becomes 240. So 240 joules. All quantities were in SI unit, so you'll get the answer also in SI unit. Okay. 240 joules is the work done by weight. Correct answer. Let us do it the other way. What is the other way? By taking the components of weight separately. Now, one of you tell me, what is the formula for weight component along the incline? Formula first.
mg sin theta, sir.
Mg sin theta. So mg is 20. Sin theta, sin 37 degrees is 3 by 5. 20 into 3 by 5 becomes 12 newtons. That's one of the components of weight. Okay. And there's another component. The formula for the other component is mg cos theta. And mg cos theta in this case becomes 16 newtons. So that 12 Newton and this 16 Newton are the two components of weight. Okay. So if you want work done by weight, you can do it this way also. Work done by the 12 Newton force plus work done by the 16 Newton force, or 12 Newton component and 16 Newton component. You can do it like that. Nothing wrong in that. Now work done by the 12 Newton component. 12 Newton is acting along the incline. Displacement is 20 meters. And the angle between 12 Newton component and displacement is 0. Okay. Next, 16 Newton component. The displacement of the block is 20 meters. One of you tell me, what is the angle between the 16 Newton component and displacement of the block?
90 degrees.
90 degrees. That 16 Newton component is perpendicular to the incline. Block is sliding parallel to the incline. The angle between them is 90 degrees. Okay. Cos 90 is 0. So this term becomes 0. It means that 16 Newton component is not doing any work. Makes sense. And the 12 Newton component, cos 0 is 1. 12 into 20 is 240 joules, which is the answer that we got earlier also. Okay. So generally you can calculate work done by a force at once by considering the total force, or you can calculate work done by components separately and add them. Okay. Not just in case of weight, this procedure is valid in other cases also. For any force it is valid. Okay, we got work done by weight. Next force is the normal force. Pawan, tell me how much work you think normal force, or first tell me how much is the normal force acting in this case?
Sir, 16 newtons.
16 newtons. Correct. Now tell me how much work it will do.
Sir, 0.
Why?
Sir, displacement की इनका normal की angle 90 degrees में होगा.
Correct. Work done by normal force. The force is 16 newtons. Displacement is 20 meters. But the angle between normal force and displacement is 90. Perpendicular dot product becomes 0. Normal force is not doing any work in this case. Okay. Next is friction. One of you tell me what kind of friction acts on the block as it slides down?
Kinetic friction.
Kinetic friction formula.
UK into N.
Mu into N. Mu is given to you in the question as 0.5. Normal force you found out is 16. 0.5 into 16 is 8 newtons. Okay. 8 Newton friction acting up the incline. Always the same 8 Newton will be acting. Because the angle of inclination is not changing, coefficient of friction is not changing. Why should friction change? It won't. Displacement is 20 meters. Aishwarya, tell me, what is the angle between friction acting on the block and the displacement of the block?
So 180.
180. Okay, cos 180 becomes -1. The answer for work done by friction is -160 joules. Okay, so gravity gave an energy of 240 joules to the block, but friction removed an energy of 160 joules from the block. That is what has happened with the block effectively. Okay, so here also friction is trying to slow down the block to prevent sliding. Slowing down means removing energy. So friction does negative work in this case, and that's the meaning of the minus sign we got for work done by friction. Okay. So what we learned today is basically how to calculate, basically what is work. Okay. What happens when work is done on a system? Positive work is done, negative work is done. If positive work is done, energy is given to the system. If negative work is done, energy is taken away from the system. So work is basically transfer of energy through forces. There are other modes of transfer of energy also. Okay, those you will learn later. So whenever you are asked to calculate work, you must be specified work done by which force you are supposed to calculate, and you will be specified. Okay, and the basic formula for work is integral F dot ds. Always say force dot displacement. Don't use the term into or anything else. Okay, integral F dot ds, and remember ds, small displacement, is the displacement of the point on which the force is acting. Where did we mention that? Displacement of the particle on which the force F is acting. And for now, in this chapter, we are only going to consider objects which are sliding, translating, not rotating. So entire object undergoes the same displacement as individual particles of the object. So for now, you don't have to bother about which point's displacement to take. You take the object's displacement. Okay. But from next chapter onwards, you will have to consider that also. Right. So general formula is integral F dot ds. If force is constant throughout the displacement, the formula changes to F dot s. Okay. Next class, we'll look at some cases where force can vary from point to point also, and how to calculate work. And then we discussed why only the component of force parallel to displacement matters for work. Okay. Force component parallel to displacement is called tangential force. And tangential force is the force which increases or decreases the speed of the particle. So that is the one which gives or takes energy away from the system. Perpendicular force, that is the centripetal or radial force, does not disturb the energy of the system. Okay, so it's only the parallel component that matters. That's why we use dot product to calculate work. And then we calculated work done by forces in some cases. Okay, all 4 forces we considered. Okay. See, Wednesday I won't be able to take a class, but I will send you a worksheet tomorrow. It will have questions based on work done by constant forces only. And there will be one section based on spring force. Okay, now some of you may be knowing spring force, some of you may not. From now onwards, that's a new force that we are going to include in our systems. Okay. In fact, some teachers teach it in laws of motion itself. No problem. We can learn it here in work, energy, and power. So there will be a section on spring force, how to calculate the force exerted by a spring, and some basic questions based on it. Okay, so solve the questions and send it to me. So Wednesday you won't have a class. Mostly I will take on Thursday. Okay, Thursday it will be from 8:30. 1 hour class I will take. Okay, thank you all. We'll continue on Thursday.
Thank you, sir.
Thank you, sir.
Thank you, sir.